Hi, everyone, and welcome to today's session on how to do advanced analytics with Dimensions data. I'm Christina Huidu, I'm the product specialist for Dimensions, and I am joined today by my colleague Simon, who has been doing some really interesting stuff with Dimensions data joined with external other source type of data. And I'll leave it up to Simon to show us magic. Simon?
Hi, thanks, Christina. So pleased to prepare for this webinar, because in doing so, I got to jump through and explore all of the different data sets available on BigQuery and just think about how they might apply to Dimensions. So that was fun, and it was a good way of justifying having fun on work time. So let me share that with you today. So today we're going to talk about joining other data sets to Dimensions. Now, Dimensions, by its very nature, is a really interesting data set to join to, and the reason for that is that it's made up of lots of different external identifiers. So if you think about the classifications that come into Dimensions, you've got FOR codes, you've got RCD codes, you've got affiliations, and where we've got affiliations, we've got grid IDs, and we've got, on those grid IDs, we've got addresses with country names. So lots of different identifiers that might potentially link out into the external world and connect up with other data sets. And beyond those links, we've also got large amounts of abstract data that we can potentially search for in terms of joining up things via a free text match. So there's another potential way of joining up data. So lots of different connections that sort of link out from Dimensions that we can explore. And on the other side, in the Google BigQuery platform, we've got lots of different data sets that have been contributed into both into the public data set side of things, and there are also other data sets that you can obviously pay to get access to. So Dimensions itself would be a case in point. So today we're just going to limit ourselves to data sets that are actually on Google BigQuery. It is obviously possible to link Dimensions up to data sets that are not in Google BigQuery, and I think Michaela in a previous example has shown you how to, say, take a table that you've got in your Jupyter notebook and push it up into Google BigQuery, so you've got a table to join to. Obviously, you can also bring data down into your workbook and join up data directly in your workbook via APIs and other things. But today, it's just going to be about exploring the data in Google BigQuery, and that, as you'll see from my screen on the right, is probably enough. So if we jump into, if you just have a look through all of the data sets that are involved in, that you can see in Google BigQuery, you can be quite overwhelmed because there's just heaps and heaps of things in here. So for instance, in encyclopedic, we've got Census Bureau data, we've got GitHub activity data, we've got international education from the World Bank, lots and lots of different things. And it's quite fun to click through these things and think about how we might tie up the information that we see in these data sets to information in Dimensions. So one way of exploring them is just going through the interface and having a look through the different data sets that you can find. But actually, once you get a handle on what's there, a better way is actually just going into your Google BigQuery interface and typing in BigQuery public data. And once you do that, you can actually have a look at the same data sets that you see in the marketplace, and perhaps even more actually, as a list. And so being able to scroll down, today we are going to look at, scroll right down, we are going to look at more details. We're going to start with looking at World Bank data. So we can look at some of the indicator data that's stored in the World Bank, like GDP. And we're going to move from there on to linking up our data to Wikidata. And then we're going to have one more example, which is looking at how we linked Dimensions data up to the Cancer Gateway. So here is Cancer Gateway. It is another BigQuery data. It's not in the public data, but all you've got to do is sign in using your Google credentials, and you'll be able to then get access to the Cancer Gateway data as well. So we're going to have a look at 3 different data sets today. Okay, so we're going to start with looking at the World Bank data. That has, we go down to, do I have that open here? Yes, I did. So if we have a look at the World Bank data, you'll see that there are, if we query that data, so we'll take our query here and we'll query the indicators data table, we can see that in terms of looking at the distinct indicators, query that result, see that there's 1,440 different indicators that we can possibly look at. And if we just drop that into BigQuery here, let's make that smaller. So see my pages. Drop that into the query. And we have a look at that. We can see the types of indicators that we are looking for are things like by country, the population of people aged 65 and above, or number of teachers, or rural population, just a wealth of different things. Percentage of trade as a percentage of GDP, just a marvelous set of things that boggles the mind. Cereal production, cereal yield, CO2 emissions, and you'll see that's just the first page. So heaps and heaps of things we can possibly look at. We are going to pick something easy to start off with, so we're going to look at GDP. But even with GDP, we can see that there are 86 different indicators that involve GDP. Have a look at those. There we go. We've got trade, broad money. We might pick this one today. GDP current US dollars, GDP per capita, and then we've got things as a percentage of GDP. So military expenditure, for instance, or gross savings, manufacturing, natural gas, so on, coal rents. So lots and lots of different things to pick, but we'll stick with GDP for now. Okay, so we've got our indicator that we're interested in. The key thing to joining up what we've got in World Bank data and what we've got in Dimensions is to be able to join up these indicators by country. And luckily, one of the country codes that the World Bank has is a 2-alpha code, which is what is in Dimensions. So we can start with joining up our GDP indicator with and to get a table that has country code in it. And then the next thing we do is pretty straightforward. If you've used Google BigQuery before and you've been querying Dimensions, you'll be quite used to this pattern. So I am looking for authors belonging to affiliate with affiliations within a particular country. So the first thing I need to do is pull up my publications table. I need to unnest the authors so that I can refer to them, and then within those authors I need to go and get those authors that have addresses. And I'm going to join that to the grid table so that I can get the country from the grid table. So Dimensions, unnesting my authors, getting my author affiliations, joining that to the grid table via an inner join. And if you're not really familiar with SQL, inner join simply means that if I'm joining that data, if I've got an affiliation, for instance, that doesn't have a grid ID, it's going to drop that from the results because there isn't a result to it. If I wanted to keep the affiliations without any links to an identified institution, I'd call that a left join, and I'd keep that information in my query. Okay, so I've got my Dimensions query. and I'm going to join that to my World Bank data. So it's as simple as now referencing my World Bank table, so BigQuery / public data.worldbank indicators data, and I'm going to inner join that to the World Bank country data, just like I did in the example above. And I'm going to restrict it to the indicator name, and the year of the indicators I'm going to choose is 2017. And why I'm choosing 2017, that'll become clear in a minute. The World Bank data, as far as I can see, was updated last in March 2019, so you can actually get GDP figures up to 2019. And I would assume that that data will be updated shortly for 2020 as well. So here it is, I've got my query. I've joined my World Bank data to my dimensions data, and I'm going to query that. You'll see that there's a nice table here now with dimensions data and GDP data side by side. Now, I probably should have sorted that in the query, but no problems, because I am using the Google BigQuery client that returns my results as a data frame. So I can sort that data frame in my Jupyter notebook. No problems at all. So you'll see what you would expect to see, United States with the largest GDP figures in 2017, followed by China, Japan, Germany, United Kingdom. So that's great. I've got data side by side. Let's create our first cross metric. Let's just have a look at the ratio of publications to GDP. It sounds pretty straightforward. And so we will create our metric. Pubs to GDP equals the number of publications for a country divided by the GDP for that country. And we will just have a look at countries for whom have produced more than 50,000 publications, because otherwise you get fairly noisy returns. And we'll sort that data by pubs to GDP. So now we see that in terms of the ratio of publications to GDP, we've got the United Kingdom, Australia, Netherlands, and so forth. So that might be one interesting way to explore the relationship between GDP and a country. Of course, that could either mean a country has a low GDP in general, or it might have a high. So you could have a country that has quite a substantial investment in research, like the United States, but has a super high GDP, so it doesn't fall on that table. So as always, any metric you create needs to be thought of in context. But nonetheless, an interesting list. It turns out that within the World Bank data, we can also look at research GDP. So one of the other indicators is research and development expenditure. Now it's a little tricky because obviously that's got expenditure on research, but also industry and development as well. And if we were looking at publications side by side, research and development expenditure, then there's a hidden variable there about how much industry development is going on within any particular country. But nonetheless, it's an indicator that we can pull out and have a look at. So all I've done to change the query above to the query we're looking at here is swap out my indicator name. So I'm going to run that. I'll get my research and development GDP as a percentage. And because it's a percentage, and this is why I've chosen 2017, because the indicators, depending on which one they are, they come through quicker or slower, depending on how long it takes for countries to gather them. I'm going to turn that percentage back into a raw number of GDP. So I'm going to join the table I had before with the GDP figures. And so now I've got a table which lists my country, my research GDP as a percentage, publications, and the total GDP. So if I want to get the raw research and development GDP, I just times the percentage by the GDP. And because it's a percentage, I divide it by 100 to get my percentage, and then I can do the same calculation as I did previously. So ratio of pubs to research GDP this time, publications divided by raw research and development GDP. I now get an interesting list where I've now got India above the United Kingdom and Australia going through. So Again, it's not a whole story and needs interpretation, but there's another example of being able to pull in world data to dimensions data. Now, a use case that I didn't have time to write up but would be really interesting here, if you're, say, a smaller country, does it really make sense to compare your publications output to the US or China? Probably not. So one thing that you might do is say, okay, well, I'm interested in comparing myself to countries that have, say, no more than 50% more or less GDP than my country. So you can actually pick the band of countries that you want to compare yourself to based on that GDP level. And I happen to know that's a real use case from some countries that do analysis on publications performance. So there is another super interesting thing that's in the World Bank data, and that's World Bank income levels. So if we look at the World Bank table, I think it's in the, double check, it's in the country summary data. So not even in the indicators themselves, but in the country summary data. And we'll just have a quick look at that. Yeah. And you can see that one of the columns is income group. And I'll just make that a little bigger so you can see. Income group. So it's the income group to which the country belongs after the country classification is completed each year. And that is super interesting because it bands countries into low income, low to middle income, and high income, which means that, again, if we join our country data across to our affiliation data, we can have a look at how many different publications an institution does in collaboration with researchers affiliated to a country with low income or lower middle income. And that might help an institution tell a narrative of how engaged it is across the world. So for instance, here, I've just, I'm counting the number of institutions coming through from these income bands up the top. And you'll notice a familiar pattern here. So I'm looking at dimensions table for publications. I am pulling out authors, but I'm interested in how those authors collaborate with other authors on the paper. So I need to pull out those authors twice. So author 1 and author 2, and I'm interested in the affiliations of each. I'm going to inner join my author 1 to the grid table so that I can select authors from a particular institution. In this case, that's the University of Melbourne. And I am going to also, oh, sorry, I'll take that back. I'm going to inner join my grid table to author 1, and that's going to be all of the authors that can possibly be in the world. And I'm going to join those authors to the World Bank country summary data based on that 2 alpha code there from the grid tables. Super useful. And then I'm going to restrict the publications I'm looking for with authors that belong to the University of Melbourne. So I'm going to restrict affiliation 2 to be the University of Melbourne. Yeah. And I'm not interested in connections where author 1 and author 2 belong to the same institution. And in fact, so that rules out collaborating with the researcher themselves and also collaborations within the institution. And let's just restrict it to 2010 and on. So when I get that, I get the number of publications by year that have been produced by different income bands. I think that is super interesting to look at. So that's a query for one institution, but it's really not that difficult to change a query from one institution to a query for all institutions in a country. So here is the same query, and then now instead of limiting that restriction on institution to grid ID, I'm going to limit the addresses to the United Kingdom, and I'm going to keep everything else in that query the same. So now I've got a query of institutions where within the United Kingdom, the Liverpool School of Tropical Medicine has produced since 2010 1,072 publications with lower income affiliations and so on. And we can see as a percentage of their total output, it's just under a quarter of their outputs involve researchers from lower income countries, which, given the work that the Liverpool School of Tropical Medicine does, is not surprising. And it's not surprising too that the London School of Hygiene and Tropical Medicine has a high rate as well. If you roll your gaze down that list, you'll see University of Oxford being fairly strong in that as well, along with Imperial College London. So there's a subtle thing we can do to this query above here, that instead of giving us the count of publications, we can look at the count of researchers that have dual affiliations to the institution that we're looking at, and also an institution in different income bands. And the way we do that is, instead of joining, looking at the connections between two different authors on a paper, we're looking at the connections between affiliations within a single author. So here I am creating affiliation 1 and affiliation 2 for each author, not for different authors. So that's a subtle change in the query, but quite powerful. So now I can ask how many researchers with dual affiliations by income band. And we can see now that not only is the London School of Hygiene and Tropical Medicine collaborating with researchers with a significant number of researchers from low income and lower middle income bands, a significant proportion of those researchers also have an affiliation with the London School of Hygiene and Medicine. What's astounding is that the numbers that come through for the University of Oxford, particularly in that lower middle band, are quite strong. So there's a story there to be told, potentially about their roads funding. Maybe that's to do it, but it's certainly not by chance that Oxford has a number that stands out as much as that, especially when you compare it to a peer institution like Cambridge. So those are quite different numbers. So there's a story that is quite easy to do on Google BigQuery. Takes not very many lines of code, but is quite a powerful insight that you can get by joining information from different places, particularly the World Bank data. So World Bank data is one source. Let's have a look at Wikidata. And before we jump into Wikidata, I need to warn you to be careful when playing with Wikidata. And the reason for that is that Google BigQuery charges you based on the data that you consume when you query a table. And if we go to Wikidata here, and I'm just going to show you the columns in a field. All of these fields are quite normal. So you've got ID and language descriptions. Then you've got site links, different sorts of labels, fields that apply to many of the entities inside Wikidata, like gender or date of birth, place of birth, country, instrument, genre, subclass, which is quite important, and we'll talk about that in a minute. So things like being able to pick all items that are of type human, for instance, or subclass of human, or as we'll look at, subclass of gene in a minute. But the killer one down here is this one called item. It just says string, but that string is a JSON object, which is super useful, but it's super huge. It's a JSON object that lists all of the data about an entity, about a particular entity in Wikidata. And the reason that is problematic, if you're not careful about it, so I'll just pull up my editor here. And let's take this query and pop that across. Oops. Pop that across there. Now you'll see that when you run things in, when you pop your code in Google BigQuery, it'll tell you how much data it's going to process. So 4.6 gigabytes is pretty fine. But let's just say we do what I often do. If I want to get a sense of a table, I just go, hey, select star from Google BigQuery, and suddenly I've moved from 4.6 gigabytes to 1.1 terabytes when run, which I may have done several times yesterday. That's not super expensive, but it's going to cost, every time you run a query like that, it's going to cost you about $5 US. So let's not do that if we don't have to. Put back in our label code. But nonetheless, here's our Wikidata table, and it's got super interesting table and interesting information in it. So even though we need to be wary about how we query it, it's worth doing. So I am now going to use Wikidata to get out a list of all the genes that I can find in Wikidata. So if we go here, this Q7187 number, where did that come from? If I go to Wikidata, it is not the one that I want, so this is gene, the male given name, but if I go to that Q number, that's the one I want. So gene, so basically this is the Wikidata ID for the concept of gene. And we can see that some of the statements that are very, just an integral part of what it is to be part of the Wikidata dataset is this subclass thing. So we can say it's a subclass of biological sequence, it's part of a chromosome. Ooh, pardon me, it has all sorts of other data on these. And each of these statements have a little predicate. Now, you probably can't see it, but in the middle of that screen, you'll see it's property P361, and they're going to be important coming up now as we chat about things. But for our query here, we can, because we've got this concept of gene, we go back to our SQL here, we can actually ask the Wikidata table, can you give me everything that is an instance of a gene? And the way I do that is I've got my Wikidata table and I unnest the instance of column, just as we unnest authors in dimensions, where the numeric ID for gene is 7187. So if I list that out and I've got my labels, what have I done? Let me get my query back. Oh, I've got that stuck in it, that's why. There we go. So I now got a list of things that look very suspiciously like genes. Now I need to be a little careful with Wikidata because I take that limit off. I now have quite a number of genes. So if we have a look down here, we've got, I think that's 1 million and something different gene names. And maybe I don't want to query 1 million things at the moment. So we'll just limit that to 1,000 for our example. And so here we've got our query. So now I'm not going to join to something structured. I'm going to search the abstracts in my publication. So with 100 or 1,000 genes from Wikidata that are an instance of gene, I'm then going to search dimensions, and I am going to just limit my query to publications of, that have the ICRP category of cancer. So I'm not spending all afternoon searching abstracts from everywhere. And I am looking for abstracts that contain the gene name that I've got from Wikidata. So I can see, and I've just done one other thing there, because I don't want to, because genes could be, SRC could be an acronym for many things, or it could be part of another word. I've just put spaces around it, which gives me a very rough and ready confidence that at least I'm picking out individual acronyms. So here I am searching my abstracts that contain the gene. I'm limiting it to publications since 2015. And when I run that, not surprisingly, you can see that the gene name that contains the most matches is 2000 is the main breast cancer gene, which I guess I was a little bit lucky to pick up in the top 100 genes, but there you go. So not a bad example. Now, where you might expand that to is if you've got a source of information that contains information on a network of genes, you might start looking for pairs of genes and how they've matched up. So you can look at the frequency of abstracts that mention gene 1 and gene 2, and you could use that to begin exploring different reactions, perhaps, between different genes. So again, that's quite a basic example of how you might use gene information. But there is just heaps and heaps of medical information that you can join it to. So let's take that gene example, and instead of looking at Wikidata, look at the ISB CGC Cancer Gateway in the cloud, which is actually not a data set that you'll see in the public data sets, but it's up here. If we go to ISB CGC, it's a huge NCI Cancer Research Data Commons. It's got heaps and heaps of stuff in about genomes and all sorts of related data, and makes me feel very aware of how little I know about biology and genetics, but super cool. Most of this information is in BigQuery, and if you do happen to know a little bit about that, then ISB CGC gives you a really good search of all the different sorts of data that you could possibly find. And what I'm interested in is just expanding on the example that we had before. We're going to look at some gene ontology data, and we're going to look at the gene ontology, which has, actually it's this one here, isn't it? You can do it. Basically, a data table of genes. So this one is quite interesting. So I suspect it's got a little bit of network data in it, which I would like to explore. So you can actually see genes that connect to, with, or from other genes. But I don't know enough about exactly what that does, but it does seem to encode a network of some type. But for this particular one, we're going to look at the DB reference. So this is one or more unique identifiers for a single source cited as the authority for the attribution of the particular gene to the database. So that's particularly interesting because that is linking back the gene to the seminal paper that defines it. And what's really nice about it is it's using PubMed IDs, and PubMed IDs, of course, are also in dimensions. So we can take our CGC genome reference table, and the only difference about using the ISB CGC tables is that you need to first authenticate with just once with ISB CGC using your Google name, and the reason that I do that, I suppose, is so that they know who you are and they can track usage. But that just gives you access to the data. Once you've got that, you can query it in Google BigQuery. So here we've got our Go table, and we're doing something fairly familiar. We're unnesting the references. So they were encoded with pipes as a list delimiter. So we will split that out and unnest that to get a list of PubMed IDs for our genes, and then we'll join it to our affiliations. And by now, this will be a very familiar pattern to you. We want to get the institution associated with those affiliations, and we're joining that table where our references equals the PubMed ID, and obviously we just need to put PMID colon in front of dimensions PMIDs because with their numbers inside dimensions and don't have the prefix. So we're matching them up, and then we get this lovely result here. So according to the Go ontology, the institution most associated with the definitive articles that define those genes is Harvard, then Tokyo, then UCL, Yale. So again, quite an interesting set of tables looking at the historical development of genes. Now, the Go ontology, you can see, is not spanking new and up to date. It was uploaded in 2016. But then again, I don't imagine the discovery of new genes is super frequent. Okay, so there's our query on ISBC. Now I want to return to looking at Wikidata carefully, exploring that big JSON item at the end here. Now this comes with warnings. Every time you touch that table, it's going to be a potentially cost you $5, but nonetheless, it's quite rewarding to do so. So one of the things that I explored quite in depth, probably last year or the year before, was being able to use Wikidata to look at awards and qualifications data. So to be able to say, okay, who's got a Nobel Prize, for instance, or who's got the Fields Medal for X, and ways of being able to bring that data back into dimensions. Now, the relationship that we're looking at, if we look at this is P166, and in Wikidata terms, the relationship P166 means has received an award. So you can see here, if we put this query in, and we're now using JSON extract to extract and process that item into queryable bits, we can see that if I query on P16, we can see if Herbert Matthews has received the Maria Moore's Cabot Prize, or Elie Wiesel has received the Prix Prize in Medicine. And not just research prizes, but order of military medals and all sorts of things you might expect in Wikidata. Now, because there's all sorts of different sorts of prizes in there, there's another relationship that we might look at inside Wikidata, and that's whether or not a prize has been endorsed or reviewed by a particular body. So one of the bodies we might look at is the International Congress of Distinguished Awards. And so we can, by using this property, endorsed by, we can actually say, give me all of the awards that have been endorsed by the International Congress of Distinguished Awards, and that's all about researchable awards now. So now we see awards that are much more relevant to a research context. And again, I'm looking at, I'm using instance of, so instance of this, what am I using instance of here? I don't think I am. But at any rate, what I am doing here is I am looking for awards that have been endorsed by the International Congress of Distinguished Awards, and that entity in Wikidata is this one. We go International Congress of Distinguished Awards, and they have a very early 2000s website displaying who they are and what they do. Lovely. So I've got my list of awards. Now, what I want to do is join that to look at those awards and find the people that come from there. So here I've got my awards, list of awards I'm looking at, and I'm going to put that into a Wikidata query that then looks at the people. So that first part that I was looking at before. So you can see the awarded property here. And just to make it easy, I'm going to extract the ORCID ID, which is also sometimes present in Wikidata, and I do stress sometimes. We're going to get out the ORCID ID as well. So we're just going to join those awards that join nicely on ORCID ID. And the reason for that is obviously that ORCIDs are also part of the Dimensions dataset. So now I've got my list of awardees. We've got Greg here. He's been awarded the Heinz Award, and here's his ORCID. So the final part in joining all of this up together is to use ORCID IDs from Dimensions, and they belong in the researchers table. So you can see here the ORCID IDs for a particular researcher ID, and you'll note that there's a column that we need to be aware of because we don't want IDs that have been made obsolete. So here it is, all one big query. We've got our awards. Then we're joining that to people to get the people out, and we're joining that to the researchers table to get some further details. So we end up with a table like this, listing out our people, what award they've got, their ORCID, and some basic data. Now you can imagine joining that up to an institution table to get a view of how many Nobel Prizes particular institutions have won, with the caveat that you're going to have to do a little bit more work, because obviously the data is not clean enough where every researcher has an ORCID. So you're going to have to do some fuzzy matching, maybe on a combination of name and institution. So you're bringing in further Wikidata fields, looking at the institution which they are affiliated with, or the place that they got their education from, and those sorts of things. So there's more work to do there, but nonetheless, you can bring in data from Wikidata joined on ORCID. You can also bring data from Wikidata in joined on Grid ID, because Grid ID is also in Wikidata. So you just need to be a little bit careful with this column, because it will start costing dollars to start querying Wikidata. So perhaps one nice way, perhaps actually probably the preferred way of developing queries on Wikidata is to create yourself a temporary table first with a number of Wikidata records that you know have the properties in them that you want to extract, and then work on that temporary table first to get the query right, because you're going to iterate over it and over it again to get it right, because this syntax is not straightforward. But once you've done that, replace your temporary table with the whole of Wikidata to get the data out that you want. And that brings me to the end of the things that I wanted to talk to you about today. So really only scratching the surface of the different sorts of data sets that you can connect up to Dimensions using Google BigQuery, and really only restricting ourselves to tables that are inside Google BigQuery at the moment. You can do a hell of a lot and take your investigation and analysis much further than just with Dimensions itself. So that is what I wanted to talk about today, and with that I will open up to any questions. By the way, thank you for sticking with me. That was 44 minutes of me just talking about SQL queries, so I appreciate you hanging on there. But if you've got any questions, we've got 15 minutes left.
Thank you, Simon. That was super interesting, and cannot wait to get my hands on that code. And as Simon said, if you have any questions, we can either unmute you or you can drop them in the chat. There is raised hand. Henrik, you have control over your microphone now. Hi.
Yes, if you can hear me, I have. Great, thank you. Thanks for a very nice presentation. So one thing I've thought about often when we work with Dimensions is that There is a limitation to identified grid institutions, it's specifically private companies. So, do you have any ideas on how to get around that? Because it's an issue when you're looking for companies in clinical trials where partners are still raw text; they're not identified as grid institutions.
Yeah, that's a tricky one. Often when I'm doing consultancy work, if I'm looking for a particular company or institution that's not in grid because it's a foundation or something that hasn't quite made its way into grid, the only thing that I've been able to do is to use the API and do free text searching for instances of its name. It's not ideal, but if you've got limited scope in terms of investigating the companies that you're after, it generally does the trick. But I agree that we've got more work to do to open up to more companies involved in the data set, because that would be super useful. I should say that brings up one other use case of connecting Google BigQuery to other data sets. And one of the data sets that sounds counterintuitive is to connect dimensions to itself. And so you can obviously use the dimensions API to do free text queries on the full text document, and then bring those results, the IDs of those results at least, back into Google BigQuery to do further querying on. That's certainly another interesting pattern there, where the API can do more things in certain instances than the SQL queries in Google BigQuery can do.
Thank you. There's one other question. Do you have a ready-made table with all of the prize winners?
I don't. Yeah, I would love to have a ready-made table with all of the prize winners. I'm thinking of doing some work on that, so I'll keep you posted. I think one of the super cool things that we could potentially do with Google BigQuery is create a list of all the prize winners such that we could see in Wikidata, but also create little monitoring tables so we can monitor the quality of the records in Wikidata for each of the prizes, and that might help to motivate friendly people to go in and improve the quality of the data in Wikidata, so that we could keep track of how many people had an orchid associated with different prizes and how many people had records that were easy to use. So I will keep you posted on that one. I think that's a super intriguing thing to do and would be super useful. You're right.
Thank you. I hope that answers your question, Jörg. If you have any more questions, that would be great. We do have about 12 more minutes.
I should say I'll make this all of these examples I've got through in a shareable notebook on Google Colab. We're just putting together a web page like we have for the API with lots of different examples, and this example will most definitely make its way there.
That sounds great. Thank you. It looks like there are no more questions. So I do thank everyone for all of your time. I hope this was as interesting for you as it was for me. And we will see you in 2 weeks.
Wonderful. Thanks, everybody.
Thank you. Bye.
No ball now.
Hey, red and black. I was going to say red and red person.